All right, welcome. In this video, we're going to be working Algebra 2 homework 12.1, which is about exponential and quadratic regression and also looking at tables of data and trying to decide what type of function matches them. Okay, that's a lot of tables, and I think hopefully I told you in class that I don't need you to do more than half, right? Do the odds, do the evens, do enough of them so that you feel like you know what's going on here. Don't beat yourself up determining whether a table of values gives you linear, quadratic, exponential, or none of the above. Now, just to remind you, linear is going to be where, when we have evenly spaced x's, the y's, continually increase by some number. So I'm going to say, all right, 14, 10, 6, 2. So I decreased by 4, I decreased by 4, I decreased by 4. I'm decreasing by 4 every time. Okay, so I'm going to say number 1 is going to be linear because it's got that constant first difference. Okay. Number 2 is going to be, all right, these x's are evenly spaced. 1/2, 1, 2, 4, 8. Okay, it feels like I'm multiplying by 2 each time. Okay, that's going to be exponential when there's a constant ratio, and that ratio is going to be 2. Okay, number 3, I have to, up and down that way. All right. Over here, I've got evenly spaced x's again, and it looks like all of these, at least for now, are going to be evenly spaced x's. So I go over here and I say 21 to 12 is -9. But then I decrease from 12 to 5, and that's a decrease of 7. So I've got -9, -7, -5, -3, -1, +1. Okay, so that's going to have a constant second difference. Let me get a little scrap of paper. Show you what I'm saying. All right. When we go from 21 to 12, that was -9. 12 to 5, -7. 5 to 0 was -5. 0 to -3 was a difference of 3. -3 to -4 was -1. And then, okay, +1. Okay. And then if we look at the second differences, these rates of change, they form a linear pattern, right? Because it's +2, +2, +2, +2, and +2. So I'm going to conclude that this is quadratic because there's a constant second difference. And then number 4, let's see what's going on here. -16, -13, -10, -7. Okay, each time I'm adding 3. Yes. Okay, so that if I'm adding 3 each time, I have a constant first difference. That's a linear function. All right, number 5, what are we seeing here? Wait, did I not? -14, -9. No, I guess I haven't done that one yet. It's okay, only a third of the way through and they're already starting to look the same. Okay, -14 to go to -9 is an increase of 5. Increase of 5, increase of 5. I'm increasing by 5 every time. Okay, that's linear. Okay, number 6. -18, -6, -2, 0, 2, 6, 18. Okay, well, I see it's decreasing and then increasing. So that's got to be probably quadratic, right? If it's going to be one of these options. So I'll go in here. Okay, pardon me, I'm just going to use the same slip of paper. -18 to -6 is an increase of 12. Then to go from -6 to -2, that's an increase of 4. -2 to 0 is an increase of 2. Then wait a second. I guess this is going to be a neither, because there, I went down by 8, and then there I went down by 2. Yeah, so I don't have a constant second difference. There's no some sort of multiplier I'm multiplying by each time. We can see that the first differences are not constant, so it's going to be none of the above. This one is neither. And, I probably won't do that to you very often. If, outside of this set of 16 practice problems, that's just not going to happen. It'll be one of the linear, exponential, or quadratic. Okay. Then 4, 8, 16, 32, 64. I'm doubling each time. I'm multiplying by 2. 64, 128, 256. If I'm doubling each time, evenly spaced x's, that would be exponential. And yeah, I've got just enough room for number 8. 1/27th, 1/9, 1/3, 1. Okay, now if you weren't sure what's going on here, 1, 3, 9, 27, each time I'm multiplying by 3 there. And you could think about each time I go to the left, I'm dividing by 3. And that's what's happening. 1 divided by 3 is 1/3. A third divided by 3 is a ninth. A ninth divided by 3 is 1/27. Okay, so I'm multiplying, got a constant ratio. This is going to be an exponential function. All right, so now maybe I can get rid of this sheet. And yeah, I'm just going to start over here. All right, for number 9, 30, 20 is a decrease of 10, but then I decrease by 8, so I need to probably, actually look at these first and second differences. It's definitely not exponential, I know that, but I'm not certain that it's quadratic because we've already seen one where it wasn't linear, but it wasn't quadratic either. All right, so that decreased by 10. 20 to 12 is a decrease of 8. 12 to 6 is a decrease of by 6. 6 to 2 is a decrease of 4. 2 to 0 is a decrease of 2. 0 to 0 is no change. And I was a little worried about that, but if we look at the second differences, that's increased by 2, increased by 2, increased by 2, increased by 2, and once more increased by 2. So it's a parabola that has vertex at x equals 2.5. Okay, so I see constant second difference. That will be quadratic. 9 is quadratic. All right. Okay, for number 10. I'm going to say, all right, 11, 9, 7, 5, 3. That feels like I'm decreasing by 2 each time. Decrease by 2, decrease by 2, decrease by 2, decrease by 2 every time. Okay, if I have a constant first difference, that's a linear function. 11, this is the exact same table that we've already worked with, I think. 1/9, 1/3, 1, 3, 9, 27, 81. Oh, it was like a little bit off. Still exponential, though. So yeah, each time we're multiplying by 3, so that's going to be exponential. Okay, for number 12, I'm dividing by 3, it feels like, right? Negative 27 divided by 3 is negative 9, and negative 9 divided by 3 is negative 3. But then this is not fitting the pattern at all, because this would need to be 1. And then it would be like negative 1, negative 1/3, negative 1/9, negative 1 over 27. I mean, I guess I could check the second differences. But yeah, that'd probably be the thing to do. So where am I? Number 12, right here. All right, so negative 9 to negative 27 would be, so I'm going to be increasing by 18. I'm going to be increasing by 6. Increase by 3, increase by 3 again, increase by 6, and increase by 18. Then I look down over here, 18 to go down to 6 is minus 12. That's minus 3. That's not constant, because this one. Okay, number 13. Okay, it's not going to be linear because 0 to 5 is not the same difference from 5 to 8. 0 to 5, that's not going to be exponential either. Right? It's not going to work. So I'm thinking, completely lost myself here. Oh, yeah, I'm down to pretty much quadratic, and I need to investigate the first and second differences. So I went up by 5, up by 3, up by 1. Okay, this is actually looking pretty good. Down by 1, down by 3, down by 5. This one is going to be quadratic because here I see a decrease of 2 in all of these. Whoops, missed one. And this table is just crammed these in too small of an area. Okay, so I see a constant second difference on number 13, so that's going to be quadratic. Number 14, if still all of these are evenly spaced x's. So 3, 0, negative 1, 0, 3, 8, 15. Okay, maybe, could be quadratic. What's it doing? It's decreasing then increasing. So yeah, I feel like quadratic's definitely a possibility. And, you know, it's got this kind of symmetry around x equals negative 1. Zeros, threes, you know, feels like maybe x equals negative 4 would give y equals 8. But let's find out. All right. 3 to 0 is a decrease of 3. 0 to negative 1 is a decrease of 1. Negative 1 to 0 is an increase of 1, increase of 3, increase of 5, and an increase of 7. Negative 3 to negative 1, that's plus 2, plus 2. Yeah, these are all plus 2s, so it will be quadratic. All right, now the last two. Looks like it might also be quadratic. Okay, they saved all the quadratic ones until the end. Okay, so 1 to 0 went down by 1. 0 to negative 1 also went down by 1. Okay, that doesn't seem right, but we'll see. Negative 2, that's a negative 1. But then it becomes positive 1, positive 1, positive 1. If we look at these, we're going to see no change here. Increase of 2, no change. So this one's going to be neither. And I guess on the ones that are neither, they want to give you one that's like maybe believably quadratic because it's got some kind of like symmetry to it, but it's not having a constant second difference. Okay, like look at this one, 9 eighths, 9 fourths, 9 halves, 9, 18, 36, 72. We're doubling each time, right? For a while, it might not be obvious that, that you're doubling because the denominator is half of what it was, but that's the same thing. So if I go from 9 halves to 9, 9 to 18, those dots are doubling. This is exponential. All right, the next problem is going to be data representing the relationship between number of hours studied and the corresponding test scores for a group of students. So we've got 4 students. And, okay, I think the idea here is that it's quadratic because more studying is good until a certain point, but then you're not sleeping, and then your score is going to go down because you're spending too much time studying. All right, find a quadratic model for this data. We're going to need a calculator. We're going to run a quadratic regression. All right. Step 1, get yourself a calculator. Okay, we've got that. Step 2 is going to be enter the data into the lists. And so I'm going to try to get this all on screen so that you can see what buttons I'm pressing, but yeah, maybe that was a little tilted. I'll get them. So I'm going to go into stat to edit the lists. Okay, so I press stat, and then I need to press edit. So I'm pressing enter. Okay, and then I'm going to put all of the independent variable values, the x values, in list 1. Okay, so that's going to be hours studied because the test score is depending on the number of hours studied. So 1, 2, 3, 5. Okay, and then the test score was 64, 86, 97, and 92. Okay, I always think it's a good idea after you type it in to just double check. 92, 97, 86, 64. Okay, good. 5, 3, 2, 1. Okay, feel good about it. Okay, now I've got the data entered, so I want a quadratic equation to represent it. So I'm going to go back to the stat menu, and we're going to ask it to calculate us the equation of a quadratic that fits the data. So we go over here to quadratic regression. We press enter. Okay, x list, y list. Are we going to need to? Yeah. Okay, we're going to maybe. Yeah, score below 70. We're going to want the graph. So, if you're working with one of these nice calculators like I've got here, that's like the color display, you can store the regression equation into y1. And I'm going to show you how to do that. We're going to call for y1 out of f4. I'm in polar mode, pardon me. I was doing some calculus. And even though in calculus you're probably not supposed to go into polar mode, okay, that's not what I wanted either. Okay, so I'm going to go back to stat calc. Yeah. Nope. Stat calculate. Quadratic regression, store the equation into y1. All right, if you're in the right mode, when you press F4, it'll bring up the y's. Okay, I want to store that in y1. We're going to calculate it, and we've got ourselves an equation. Okay, so ax squared plus bx plus c. You can kind of see that. So for 17, I'm going to say score y is equal to negative 4.818 x squared plus 35.855x plus 33.127, where x is the number of hours studied and y is the score. And on this equation, that's like the predicted score. All right, so now what am I doing here? Okay, 18, what would be the expected test score with no studying? Okay, so no studying is x equals 0. That would lead me to believe that that would become 0. This will be 0, 33.127. Okay, no studying, we're not predicting you're going to get a very good score. Number 19, according to the model, what amount of studying would optimize a student's score? So we want the greatest possible score. We want the maximum possible value of y. So we're going to use the graph. We learned about this a little bit. So we're going to graph, and this is just not going to be it at all. So what we can do, since we've already got the stat points, the stat lists populated, we can zoom to stat. And I'm not sure if this is going to work because I turned the stat plot off this morning. Yeah, that didn't work at all. We're just going to need to go ahead and adjust our window. Okay, y is score. So I'm not going to really be interested in any score less than 0. In fact, I probably don't even need to care about any score less than 33. So I'm going to go 33 up to 110. Scale of maybe 10, and then I don't know, 10 hours of studying is definitely too much, and we can already see that it started to diminish after 3. So maybe I'll say 8, not 18. And now I've got a window that will give me a little bit more of what I'm looking for. Yeah. So I'm going to calculate the maximum. I'm going to go till I'm sure I'm to the left of the maximum, and then to a point that I'm sure is to the right of the maximum. Give it a guess. All right. 3.721 hours gives you a score of 99.8, supposedly. I think that might be an oversimplification, but I'm going to say that happens when x equals 3.721 hours. Don't let it be 3.722 hours, or else you're going to be, sacrificing score. Okay, according to this model, what amount of studying would cause a student to score below 70? Okay, so we're interested in where y is equal to 70. And we're going to solve that back for probably a couple of x values. So I'm going to graph y2 equals 70 and see, okay, they ran into each other. So I need to find the intersection. I'm going to calculate the intersection between blue and red. Yeah, I'll give it a first guess over here. That's 6.209. And the other intersection is going to happen. Let's calculate the intersection. First curve is blue, second curve is red. I'd give it a guess of 1 hour. And okay, yeah, 1.233. Now, the score is going to go below 70. The score is blue and 70 is red. The score is below 70 here and back over here as well. So that means that if I spend less than 1.233 hours studying, that's over here, or more than 6.209 hours studying, I'm going to expect, blue to be below red, and as a result, my score to be below 70. So I would say less than 1.233 hours, or more than 6.209 hours would cause a score below 70. All right, and that's 20. Right. Number 21, we've got bacteria. That's always exponential. So scientists are testing antibiotic against bacteria. And number of bacteria in was measured at various times, t days after they hit it with antibiotic. So, all right, 21. Suppose the relationship between number of bacteria remaining and time is approximately exponential. Find an exponential model for the data. Okay, so we're going to need to go quit, clear that out, and we're going to go over here and edit the lists. Wait, I'm calculating, got ahead of myself. We're going to edit. We're going to type in these values. Okay, oh, and also, if you need to clear a list, what you can go do is you can select L2, and you can press clear, and then press down, and then it'll get rid of all this stuff. Don't press delete. Okay, I'm going to have to send you the stat teacher if you delete one of the lists. I don't know how to undo that. Okay, it's been so long since I've taught statistics that I don't even remember. 0.6, 1, 1.4, and 1.9. Okay. And then the n values, the number of bacteria remaining, which I'm going to put in Y2, that's going to be 44, 29, 13, and 7. Okay. We've got those entered into our list. We're going to stat calculate. They're saying exponential, so I need to go down to exponential regression. X list L1, Y list L2. We don't do frequency lists in the stat class, but I am going to store the regression equation into Y1. And then here we've got it. Okay. So I'm going to say, all right, 21. I guess you would probably stand to look at my calculator. All right, A times B to the X. So N equals A, 111.313, times B to the X, 0.231, to that, but, X is now T. Okay, so I've got my equation. Yeah, there we go. Approximately how many bacteria were there at the start of the experiment? Okay, start of the experiment is t equals 0. So I'm going to plug in directly for t and get n of 0 equals 111.313 times 0.231 to the 0. Okay, anything to the 0 is going to be 1. So I'm going to have 111 bacteria, okay, assuming that we've just got whole numbers of bacteria and they're able to count that. Scientists assume all the bacteria will be gone when the model shows the number of bacteria going below 1. Approximate the amount of time it will take for all the bacteria to be killed. Okay, so I need to know where does n equal 1. So what I'm going to do is I'm going to go back over here. I've already stored the regression equation into y1, and I'm going to say y2 is going to equal 1. Okay, I'm going to zoom to the standard window. Okay, that blue is my exponential decay. You can see the bacteria is pretty effective, right? It's rapidly killing off bacteria to the point where there's pretty much none left very soon, I guess after a few days. But we're going to calculate an intersection between blue, let's see if I can see it, yeah, there we go, blue, red, give it a guess. There's only one intersection, it doesn't really matter what your guess is. It's going to be t equals 3.213. And, okay, that'll be the amount of time it will take for all the bacteria to be killed, because, like, at this point, we add zoom in on that situation right there. Yeah, after this time here, the bacteria went below 1, and if there's less than 1, I guess that means there's none left. Okay. All right, on the back. Two more situations. An object is falling from the sky. Projectiles move in parabolas. Okay, so it's going to be, a quadratic regression, it looks like. Suppose the relationship between height and time is approximately quadratic. And if there was no air resistance, it would be exactly quadratic because of gravity. at least based on my understanding of science, which is not that much. But there's other things like air resistance, wind. Who knows? Maybe the object was falling and a bird flew into it or something. It could be, outside forces. So we're going to find a quadratic model for the data. I'm going to go a little faster this time. So I'm going to go stat, edit the lists, clear them out. And 1, 4, 6, 9. 1650, 1500, 1300, 850. Okay. Well, just believe in this quadratic. So then we're going to stat calculate a quadratic regression. We're going to store the equation into y1, and we're going to calculate. All right. This seems too good to be true. I have a feeling this is exactly quadratic, but that's okay, because what we learned is, earlier in the course, is that in order to fit a quadratic to data, we have to solve a 3x3 system. So we could really have chosen any of these 3 points. And yeah, and I can see, yes, it was just dropped from something in the sky because of that 0. If you've taken physics, then you know about that. If you don't, then just keep signing up for those science classes and working as hard as you can. You'll understand that in the future. So I think because the middle, it's like initial velocity. And I understand it in terms of calculus, but physics in other ways. So 24, I'm saying height is equal to negative 10t squared plus 0t, because b was 0 down there, even if you can't see it because there's horrible glare, plus 1,660. Okay. What was the height of the object at t equals 0? That would be h of 0 equaling, we plug in 0 wherever we see t, 0, 0, 1660. Okay. In terms of meters. Okay, based on the model, assuming the object was released at t equals 0, was the object dropped, launched upwards, or propelled downwards? Oh, I know how you could figure this out not being a physics student. What we're going to do is we're going to go graph this thing. And we're going to have to really adjust the window, though. Right? Oh, interesting. Just have faith. It's going to be all right. That basically means negative 10. So we're going to go, and I think I'm going to let x run from I don't know, negative 10 to 10 maybe. It looks like a pretty decent. Okay, y doesn't need to go below 0 because the ground level is 0. It's not going to go underground. Y maximum, maybe I'll just say 2,000. Okay. But actually what we know is that the object was released at t equals 0. Maybe I go over here and I say, t starts at 0. Okay? And although I guess this is height versus time, not really actually a graph of the position of the object, if it was launched upward, height would increase a little bit after the beginning. If it was propelled downwards, we'd see a negative slope. It would already be pushed it down. So since it's flat, that means at the beginning, when you let go, it had no velocity, and then the velocity increased because gravity was pulling on it. So I'm going to say, I did not approximate the time at which the object hits the ground. Okay, so that was 26. I'll come back and do that in a second. 27, I'm going to say dropped, but I'm also going to say that's kind of beyond the purvey of Algebra 2. We're not going to really have to worry about that, I don't think. I'll let your physics teacher try to convince you of why these things are true. So approximate the time at which the object hits the ground. That's something I want to know. When does h equal 0? What t gets me, h equals 0. So I can't quite see it. I want to get rid of this 1 because that's not going to be useful to me. And then I'm going to calculate a 0 on the graph. So on the window, I need to go a little bit bigger than 10. Maybe I go 20. Boom, there we go. All right, we have a 0. But I don't know if it would work, but maybe I'll go, negative 100 there to give myself a little bit more room so I can go to the left and to the right of the 0. I think that's the issue, is that we need to calculate a 0. We're going to go get a marker to the left of the 0 and a marker to the right of the 0, then give it a guess, and I get 12.884. Seconds. Okay, that's how we did that one. Okay, the last one, we've got population of animals. Okay. oftentimes modeled with exponential functions, but I'm just going to tell you that's not really realistic because we live in a very finite universe. And maybe I'll show you what I mean here, that there's actually a different type of relationship that's much more likely that a population will follow. It's called a logistic model, and you may have heard about it in biology or human geography or something like that. But suppose the relationship between the deer population and time is approximately exponential for, near time frames. Find an exponential model for the data. Sure. Stat, edit the lists, clear them out. Okay. 1, 3, and 4. And then list 2 will be the number of deer, 61, 130, and 200. Okay. Then we're going to find an exponential model for the data, so that's going to be do a regression equation, calculate an exponential regression, list 1, list 2. I don't know if we're going to need to, but why not store it in Y1 if we can. And then I've got 40.856 times 1.482 to the t. Yeah, time in years. I use t for time. For 28, I'm going to have, population P of t equals 40.856 times 1.482 to the t. And in my class, you're welcome to just cut off at 3 decimals or carry all of them. I really don't care. We're only going to be checking to see, we're only checking to see if you're accurate up to the first 3 decimal places. All right, number 29, and that's the last of them. Approximately the time at which the population of deer went over 100. Okay, so we are seeing exponential growth. Okay, I didn't even stop to think about the fact that the number of bacteria was exponential decay because the multiplier was less than 1. Okay, we saw it on the graph. I just didn't even think to mention it. Is that it? No. Where is it? Here we go. Pardon me. All right, so when did the population of deer go over 100? So, no, that's still not the right one. Here it is. Pardon me. So I'm going to graph 100 also. Probably manipulate the window from 0 to 200. That's not what I need. Time in years is seeming like it's going 1 to 4, so I'll do 1 to... went over 100 and probably just be 1 to 3. And then y is going to need to go 0 to 200. Okay. And then that's my exponential growth curve. We are seeing some growth. We're seeing an intersection. We're going to calculate it. That's t equals 2.276 years. So I'm going to say 29. P of t equals 100 at t equals 2.276 years. Okay. And that's all for this homework. That's going to be all for this video. Thanks for watching.